Okay, so now we're going to move towards some of the applications of the orthogonal projections. Okay, we will start with what do you call the so-called notion of what do you call the best approximation. In other words, that what do you mean by the best approximation? By best approximation, I mean that imagine this is a space, what do you call U? So this is space U, and let's say that this is U perp. This is U perp. They both agree at 0, and say you have an arbitrary vector, what do you call V, from the inner product space. Okay, arbitrary vector V from the inner product space. Now in this subspace, which is a finite dimensional subspace, I would like to find a vector. Okay, I would like to find a vector that approximates the vector V. In this subspace, I would like to find a vector that best approximates, what do you call, the vector V. There can be a lot of vectors, and what do you mean by the best approximation? The difference between, in other words, the difference between vector V and the vector U from, what do you call, a space U should be as small as possible actually. Okay, so the U for which, you know, this distance, this number is the smallest, is going to be the best approximation of V in the space U. So now it turns out that what we can show, that if you have a vector V and a subspace V, subspace U, then the best approximation of V in the subspace U is basically what do you call the orthogonal projection of V onto U. Okay, the orthogonal projection of V onto U. Okay, in other words, if you compute the difference between V and the orthogonal projection of V onto the space U, and then compute the norm of it, this norm is less than or equal to all other vectors U from, what do you call, U. So in other words, this is the vector that is closest to the V in the space U actually. Okay, and this theorem is called the best approximation theorem. Okay, so this theorem is called best approximation theorem. Okay, so what does a best approximation theorem says? It says that, imagine, let me write it precisely, that if U is a finite dimensional, it's a finite dimensional subspace of finite dimensional subspace of the inner product space V, then if you pick any vector from V and ask, from the space V, and ask that what is the best approximation of V in the space U, then that best approximation is the orthogonal projection of this vector V onto the U actually. Okay, then the orthogonal projection, okay, the orthogonal projection of the vector V onto U and its difference, okay, its difference with V. So in other words, the difference between V and the orthogonal projection of the V into the subspace U, in the sense of the size, that the difference of these two vectors is less than or equal to any other vector in the space what do you call U, okay? What do you call in space U? So in other words, if you compute the V, difference between V and the orthogonal projection of V onto the U, this difference is going to be less than or equal to V minus, what do you call, V minus any other vector in U actually. So I'm going to say PUV is really the best approximation of the vector V in the space U. Okay? Now you going to have moreover, if this U is basically the orthogonal projection of V itself, then you're going to have the equality between both. Then you have equality in above. So then these both would be equal actually. Now this has a lot of interesting, what do you call, applications. So for example, one particular application is going to be that if you, for example, consider any function and you say a single variable function, okay, and you try to approximate that single variate function through polynomial. Now you know that you have Taylor approximation, okay, but we're going to show that by the orthogonal projections you can get even better approximations than the Taylor approximation actually for any given one-dimensional function. So we will do one example based on it. Okay? Alright. So what is the next thing? So let's quickly prove this result. Okay? Let's quickly prove this result that why the difference of V from its orthogonal projection is less than or equal to the difference of V from any other vector in U. Okay? Why this is the case? This is the case because every V can be written as the orthogonal projection of V plus V minus the orthogonal projection of the V, where this V is from U and this V minus difference is from the U perp actually. Okay, so this is something that we know. So if I compute, for example, V minus the difference of the orthogonal projection of the V onto the space U, its square, okay, then this can be written as what? Okay, this can be written as what? This can be written as this can be less than or equal to V minus the orthogonal projection of U minus V square plus a quantity V minus the orthogonal, say V minus the quantity U square actually. So this side is bigger than this because in this side you have this additional term actually. Okay, in this additional term. Now both of these, sorry, if I write the PU of V, okay, so orthogonal projection of U onto V minus U actually. Okay. Now what we can show, or what we can basically do, that this vector, okay, this vector, you know, these two vectors must be orthogonal to each other actually. Okay. So let's calculate this norm. Let's calculate this norm, or maybe I can write, for example, this norm as norm of V minus U of V square plus, so if I, for example, add one more term into this side, so this would be, so this will make the other side bigger actually, U V minus U square actually. So if I add this term into, for example, this side, so this sum would be bigger than or equal to this side actually. Now, what we can say about this this term actually. Since, okay, you can check actually that this pu of v minus u belongs to u perp. Okay, this pu minus v, no, it belongs to u actually. It belongs to the space, what do you call u? Why this belongs to the space u? Okay, it is pretty much obvious. PUV is a vector in u, and u is a vector in u actually. So their difference is also going to be vector in u. So since this is the case, this is a vector in u. Okay, since this is a vector in u, and v minus PUV is a vector in u perp. So these two vectors must be orthogonal to each other. So if they are orthogonal to each other, I can apply what you call the Pythagorean theorem. So the Pythagorean theorem would be that this is going to be P u perp v plus P u perp v minus u square actually. Okay? P u perp v plus P u perp v minus u square, because if you have two orthogonal vectors, then x plus y square is equal to norm of x square plus norm of y square. Okay, so you're going to get this. So this is same as norm of v minus u square, and this proves what it claims, that the difference of v, the best approximation of v in the space u is the orthogonal projection. Why it is the best orthogonal projection? Because this is a vector that is closest to v, okay, in the norm. All other vectors in u have their difference is the difference of their norm is bigger than or equal to what you call this difference actually. So this shows that you can treat the PUV as the orthogonal projection. Okay, and equality is going to be, you know, equality is trivial actually, that if you take u to be PUV, then, you know, both sides are equal actually. Okay, so this really completes the proof of the theorem. Okay, this completes the proof of the theorem. If I make a picture of it, I can also make a picture of it. So I have vector v, and this is the orthogonal projection of the vector v. Okay, and so for example, if I take any other vector u, okay, if I take any other vector u, then the distance between this vector and this term, so this must be less than or equal to this distance between the vector PUV is going to be less than or equal to this actually. So you can picture this picture in such a way that if you have, for example, this is the vector, okay, so this is vector v, so this is vector v, and this is the orthogonal projection of it actually. Okay, so this is vector v and this is orthogonal projection. So this distance, okay, must be greater than or equal to any other distance, any other vector u actually. Okay, any other vector u. So in other words, the distance between v and u is going to be greater than or equal to the distance between v and its shadow orthogonal projection. So these are the two distances. This is one distance, okay, and this is other distance actually. So this distance is greater than or equal to this distance actually. So I hope this is making sense to you, and you can also see this picture from the book actually. So I can make a clarity. This is the straight perpendicular distance, and this is really kind of a tilted distance actually. Okay, tilted distance. So this distance is bigger than this distance. Now this statement can be also interpreted as following actually. So here's a remark. Here's the remark. Okay, what is the remark? The previous statement can be written as that imagine you want to find the distance between V and the subspace U. So how you can find the distance between V and the subspace U? The distance between V and the subspace U is going to be the minimum, okay, is going to be the minimum distance between the vectors V minus U, okay, where the U are from the U. In other words, take the all vectors from U, compute their distance, whatever is the minimum is going to be the distance between the vector V and the space U. And this, really vector is, this minimum distance is really the orthogonal projections. In other words, this distance between V and U is really V minus the orthogonal projection of U onto V. So the minimum of the distances from V to U, where the U are from the U, is equal to the V minus the orthogonal projection actually. So hence, you can also treat this V minus P of U, V, or its norm as the distance between V and the subspace U actually. Okay, this is very much interesting. What do you call the standard way to define the distance between a set and an element actually. So the distance between the set and the element is the set of all, minimum of the all distances between that point and the element of set actually. Okay, so the distance between V and the subspace U is going to be the minimum of the distance from V to the all vector U, but this minimum is actually orthogonal projection actually. This distance is orthogonal projection. Okay, so let's take an example. Let's take an example. Consider a matrix A, which is an n by m matrix. N by m matrix with entries from F actually. Okay, with entries from F. And say the rank of this matrix is really, what do you call, R. Okay, for the rank of, say, this matrix A is R. So the number of the independent rows or columns in the reduced echelon form is equal to R. Okay, that's what the definition of the rank is. Now suppose that M is, so let M is smaller than N. In other words, there are, less columns than rows actually. Okay, there are less columns than rows. And say you take U to be the null space of the A. Okay, let's take the U to be the null space of A. Then the question is, if I take, say for example, a matrix or a vector, okay, then what would be the minimum distance between V and the null space of A actually? Okay, so let's take, for example, a vector. So let's take a vector V from Fn. Okay, then I know that this V can be written as the orthogonal projection of V onto the null space of A plus V minus the orthogonal projection. Okay, you can write it in this manner. Obviously this belongs to the space U and this belongs to the space U perp actually. Okay, this belongs to the space U perp. Now let's calculate the distance between V to U. Now what would be the distance between V minus U perp of V actually? Okay, what would be the distance between V minus U perp of V? But I know that I minus P PU is equal to the orthogonal projection of U perp. So the 2 norm of V minus PU of V is going to be the orthogonal projection of what do you call U perp onto V. Okay? This is what it is going to be. So this is really what you call the distance. You can also treat this as that this quantity is the distance between the vector V and U. So the distance between vector V and U is the orthogonal projection of V onto the U perp. But what is U perp now? U perp is really, you can say that it is the column space of A star. So if U is null of A, then U perp must be the column space of what do you call A star. Okay, and say let U1, U2, so on and so forth, UR, okay, be the UN minus R, UR be orthonormal basis. So it's the orthonormal basis for the column space of A star. Okay, so if this is the orthonormal basis of the column space of A star, then I can directly calculate this value. In other words, the distance of the U and the the distance between the space V and the U is equal to PU perp of the V, okay, and then the orthogonal projection of PU perp on the V is going to be equal to, okay, is going to be equal to what? Okay, is going to be equal to is going to be, so think about carefully about it, that maybe it's a square, the distance of the square is maybe, so this is going to be equal to the square root of, okay, this is going to be equal to the square root of the sum that goes from I equal to 1 to R, okay, and the inner product of V with the conjugates of U, the inner product of V with the U's actually, which is going to be equal to UI star V. UI star V. So this is really the minimum distance, or the formula for the minimum distance between the V and the null space of the U. Okay? Null space of the U. This is an interesting example. I would like to prove quickly a little theorem, a very interesting theorem, and then we will get to the two very interesting applications of the orthogonal projection side. So let's prove this first theorem. This theorem is about the normal equations. So we know that usually whatever we have considered here, we have always taken, for example, this U1, U2, UR as the orthonormal basis of what you call V. So now if I take a subspace, okay, whose basis is not orthonormal, then how to find the orthogonal projection? The answer is simple. One thing you can do that, okay, take that non-orthonormal basis and through the Gram-Schmidt process create an orthonormal basis out of it, because we can always do it actually. The other way could be to solve these normal equations. Then you don't have to do this Gram-Schmidt process in order to convert the bases of the subspace, which are not necessarily orthonormal, into the orthonormal basis actually. Okay? And hence find the orthogonal projections. So the next result is about what do you call normal equations, which is a way to find what do you call the orthogonal projection for a subspace whose basis is not necessarily orthonormal. Okay, not necessarily orthonormal. So you say that let U be a finite dimensional, okay, it's a finite dimensional, okay, subspace of V, subspace of this space V, with bases, just bases, not necessarily orthonormal bases, just bases, okay, U1, U2, UR, or you can say that U is the span of these vectors actually, okay. Then the question is how to find the orthogonal projection of a vector V from the space V onto such subspace, okay, onto such subspace actually. As I said, one way could be that, okay, take this basis and turn it into an orthonormal basis, okay, turn it into an orthonormal basis, and then we know the formula for computing this. But if you don't want to do the Gram-Schmidt process and turn it into an orthonormal basis, then there is a shortcut for finding the orthogonal projection actually, okay. Obviously, orthogonal projection of V onto U is an element in U, okay. So if it is an element in U, you must be able to write it as the combination of these vectors. So this is what you call I equal to 1 to R, okay, Ci and UR, okay, Ci and UR. Question, how to find these Ci? Where you can very easily find this Ci by solving the following system of equation, okay, where Ci is solution to following system actually, okay, solution to following system, solution to following, we call them normal equations, following normal equations, okay. What are those normal equations? So compute the inner product of U1 with the U1 with U2 with U1 up to UR with U1, okay, up to the inner product of okay. So this is, the next is going to be U1, U2, U2, U2 up to UN, U2. And finally is going to be UN, U1, UR, U2, UR up to maybe UR. Okay, this is what that's going to be times C1, C2 up to Cn. Okay, equal to what? Equal to VU1 VU2 up to VUR actually, okay? Inner product of VUR. So solve this system of equation. You're gonna get constants. Once we have these constants, your orthogonal projection can be written as what do you call the linear combination of CIs, so linear combination of UIs actually, where UIs are not necessarily what do you call, so UI is not necessarily are not